So let me start by apologizing because of this technical issue. Also, let me apologize for the change of title and abstract, and let me thank the speaker, the organizers for the invitation to let me speak despite all these difficulties. So I will be talking about. Okay, yet another one. Thanks. And how does it work? Okay, so I will be discussing non-abelian discrete gauge symmetries motivated by string theory, but in a language which is general enough to apply to field theories as well. And this is work recently appeared in collaboration with Miquel Berasaluce Gomez, Fernando Marchesano, both in the audience, and also Pablo Cámara. And it was partially inspired by generalizing earlier abelian models developed in collaboration with Miquel and Luis Ibáñez and Pablo Soler. So discrete symmetries are very important in particle physics, and in particular in physics beyond the standard model. For instance, many discrete symmetries are proposed to prevent dimension 4 proton decay in MSSM, and like R parity, baryon triality, and generalizations thereof. Also, flavor symmetries, both abelian and non-abelian, are often invoked to explain and reproduce Yukawa textures. So it's a key ingredient that could be relevant for physics at the next energy level. So it's worth thinking about them from the point of view of fundamental theories like string theory or theories of quantum gravity. Now, quantum gravity does not like global symmetries for different arguments. For instance, in string theory, you can do microscopic perturbative arguments using worldsheet theory. But there are more general arguments using black hole evaporation, in the sense that if you have some black hole which carries some global charge, it can evaporate democratically and the local charge is lost, which means that there are quantum gravity effects that violate these global symmetries. So exact symmetry should be gauged. Is there any way in which I can get rid of this? Clicking here? No? Okay, thanks. Again. So exact symmetry should be gauged. And the key point is that gauge charge is measurable from infinity. So you can run through this black hole argument, and at any moment you can just surround or lasso your black hole and check what charge it carries and how it goes away from the black hole when it evaporates. So you can track it and it cannot be violated. This argument is easy to understand for usual continuous symmetries, but it also holds for discrete gauge symmetries. You can measure discrete charges carried by a black hole or any charged particle by lassoing such a point-like object with a charged string, which is always available in these theories, and you can measure the holonomy or the phase that is picked up by the string in this process. So you can measure the charges at infinity because it's a gauge charge, no matter whether it's continuous or discrete. So it's a good motivation to start thinking about discrete gauge symmetries and how they are realized in string theory. So in fact, this can be easily understood from field theory, just understanding or regarding a set n abelian symmetry, and that's the prototype case of discrete gauge symmetry, just an abelian case, as a U1 continuous symmetry which is Higgs down by a field which carries charge n. So you can start with the Lagrangian for a gauge field and some scalar of charge n, and you just focus on the phase, which is the relevant degree of freedom. So let's call this phase phi, and this is the relevant part of the Lagrangian, and the charge n of this field is encoded here. The gauge transformation of these fields is just the standard gauge U1 gauge transformation for the gauge field, and then a shift of n units of the gauge transformation parameter for the phase, which encodes the fact that there is a charge n here. So this theory with just one axion-like scalar, axion-like in the sense that it has a shift symmetry, and a U1 gauge field can be dualized, as nicely described by Banks and Seiber, to a BF theory in which the scalar is dualized to a 2-form. It has this kind of Lagrangian, and in here the set n symmetry, the order of the discrete gauge symmetry, is manifest in the coefficient of the BF coupling in some suitable normalization that I will not enter in. This kind of description is very, in terms of BF theories, is very useful in string theory because it appears in several contexts manifestly in this fashion. For instance, when studying compactifications of p-form fields on Calabi-Yau or other spaces with torsion homology classes, one sees manifestly in the dimensional reduction that this kind of structure appears, and one sees that there is a remnant set n symmetry associated to the order n torsion classes, and this was done by Cámara, Ibáñez, and Marchesano in the Ramon Photons paper. In a more manifest setup, perhaps, which is the work that we did with Miquel, Luis Ibáñez, and Pablo Soler, this kind of situation is realized in terms of okay, yet again, in terms of massive, it's realized by really. Is realized by massive UAMs. Oh. Is realized by massive UAMs. Okay. It's realized by massive UAMs on D-branes, essentially because they contain this kind of BF couplings for the Chern-Simons, terms that they have in higher dimensions, and it's a matter of what kind of cycle they are wrapping, whether you have these discrete symmetries or not, and you can apply that those arguments to look for phenomenologically interesting symmetries like R parity or baryon triality in MSSM-like models, and Berselekes will be discussing about that in his talk. Now, to find the non-abelian generalization of this way of generating discrete gauge symmetries, it's useful to rephrase this set abelian case of certain symmetries in a language which encodes or makes manifest certain ingredients, and in particular what are the relevant building blocks to generate this discrete symmetry. The first ingredient or building block is the existence of axion-like fields, axions not in the sense that they couple as the Pechi-Quinn axion, but rather as fields which have a shift symmetry, or if you wish, they have only derivative couplings in the action, so they don't have a potential, and there is some isometry in moduli space. You can shift them, and that's a global symmetry. And they have a periodic identification of the field is identical to the field plus 1 in some convenient unit. So in a sense, this phi parameterizes the real line, which is where the field is taking values, and this field identification defines a lattice of identification, and the unit cell is essentially a circle. Okay, that's the first ingredient. The second ingredient is the existence of a gauging by a U1, in the sense that there is a U1 gauge symmetry acting on the gauge potential, but that is also acting simultaneously on this scalar, on this real line, and it's acting in such a way that it shifts the scalar by n times the gauge transformation parameter. And this n is crucial in the sense that it defines a winding number in the embedding of the U1 associated to the circle associated to the U1, how it's embedded into the circle parameterized by this action. Okay, so basically this when you go around the U1 circle once, you are going around the circle of this scalar phi n times. So in this language of having the scalar parameterizing the real line, this identification or this gauge invariance is defining some lattice which is not by integers but rather multiples of n. Okay, so that's the picture. This is the real line where the scalar takes values. Okay. Okay. This is the basic identification period, field identification, and this is the identification implied by the U1 gauge symmetry. So the discrete gauge symmetry appears due to the existence of field identifications, which are gauge symmetries in the sense that it's an equivalence of field configurations, which are not implemented by the U1 gauge transformation. So essentially, the certain symmetry is the quotient of these two lattices, the lattice of U1 gauge transformations modeled out by the lattice of field identifications. Right? Vice versa, it's really the other way around. So it's the lattice of field identifications by the action periodicity quotiented by those U1 gauge transformations taken care of by the U1 gauge symmetry. So one can generalize that very easily and think about the case with multiple U1 symmetries. You have a lattice of some Rn dimensional space, which corresponds to having many scalars. Each one of them has some periodicity of 1 in the different directions, so you have a multi-dimensional lattice, and then you have a gauging by several U1s encoded in this partial Lagrangian here, which means that when you do the gauge transformation of the U1s, you are translating in some lattice in here, and in particular defining some sublattice. Okay, so you can obtain the non-trivial discrete gauge symmetry as the quotient of the large lattice, or the more refined lattice modeled out by the less refined lattice. Okay, so the field identifications modeled out by those identifications taken care of by the U1 symmetries. And this kind of description can be generalized very easily. instead of thinking about just directions which kind of commute are orthogonal to each other, you think about non-abelian actions. You think about fields which have shift symmetries but which are non-commuting. So the moduli space of these scalars is not just a product of circles, but rather it's circles fiber over other circles. So as you move around in different directions, you don't come back to yourself, but rather to some other transform point. Okay, so you can think about these non-abelian actions. You can write down L Lagrangian, which corresponds to gauging these non-abelian isometries, and you have complicated transformations that kind of express this quantitatively, this idea. And again, what you will find is that the discrete symmetry is the lattice of field identifications modeled out by those identifications implemented by the non-abelian gauge symmetry involving the gauging. Okay, and one can easily construct very explicit examples. For instance, construct an axiom moduli space which is a twisted torus, so a circle which is fiber over other circle directions, and then you can study these superlattices and find realizations of, for instance, discrete Heisenberg groups, which are defined by these kind of commutation relations. Okay, now that we have this understanding of non-abelian discrete gauge symmetries in field theory, one can go to string theory and see whether they are realized or not. And there are several ways they can be realized, and we studied several classes of models realizing them in our paper. So the first one of them is to consider, generalizing the work by Cámara, Ibáñez, and Marchesano, is to consider compactification of p-forms on Calabi-Yau spaces which have torsion homology with relations among them. And eventually these relations, that I will quantify later on, encode the fact that there is non-abelianity in the action moduli space in essence. So the basic idea in the abelian case is, imagine that you start with a type 2b compactification on a Calabi-Yau with torsion 1 and 4 cycles. So there are classes which are not 0, but a multiple of these classes is equal to 0. So you can start wrapping objects there to detect the existence of charged particles and strings, which is a signal of the existence of the discrete symmetry. So wrap D1 branes produce set k on these torsion 1 cycles, produce set k charged particles, and wrap D5 branes on the dual 4 cycles produce set k charged strings. And the existence of these objects implements at the level of 4 dimensions the existence of this discrete symmetry. Now, more formally, one can introduce an exact 2 form and a non-closed 1 form which satisfy this relation, which correspond to non-harmonic forms that in a sense are encoding the existence of a massive U1. The harmonic forms would encode massless U1s, and non-harmonic forms encode the existence of some massive U1 forming here. And the presence of this k in this relation is telling you that there is some remnant set k which remains in the theory. So you can do the dimensional reduction of the Ramon-Ramon 2 form to display the existence of this gauging structure using these forms, and in particular one see that in the Kaluza-Kren reduction you can point the direction of DC2 in the direction of d phi, time, where phi is some scalar times B2, or some 4-dimensional gauge field times B2, and essentially one can see in this structure that there is a gauging. So when you do a U1 gauge transformation, you have to shift the scalar, which is the key ingredients that we had before. This is the abelian case. Now one can go to a non-abelian generalization, and the simplest realization is pretty old. It was developed by Gukov, Rangamani, and Witten in the context of ADS-CFT. So already at the time, for very obscure reasons, they realized some non-abelian gauge symmetry that appeared in a particular setup, and they realized that basically it was coming from torsion forms. So we just rephrased it in our language and checked more explicitly that it really happens. So the basic setup is, again, you start with type 2b models on a Calabi-Yau with torsion 1 cycles and dual 4 cycles, and 3 cycles and dual 2 cycles. And the dual 4 cycles are intersecting over dual 2 cycles. So it's a mess of a combination, but there exists Calabi-Yaus like that. Okay. So wrapping D1 branes and F1 branes on the 1 cycles and D3 branes on the 3 cycles give charged particles, and wrapping the dual objects D5 branes, NS5 branes, and D3 branes on the dual cycles give charged strings. So in general, each one of these objects will produce a set k abelian symmetry, but there are string effects that make the whole structure non-abelian and non-commuting. And basically the idea is that if you take D5 branes and NS5 branes wrapping on these cycles, they produce strings in 4 dimensions, and when you cross them in 4 dimensions, there are new strings which are created in between by the so-called Hanani-Witten effect. There are D3 branes which are created in between, wrapping precisely the 2 cycles over which the 4 cycles are intersecting. And the existence of this creation, the creation of these strings in the middle, is a clear signature of non-abelianity in the structure of discrete symmetries. Okay, so that's a hint that this kind of torsion cycles with non-trivial intersection patterns realize these non-abelian gauge symmetries. And in particular, one can take this language of forms and propose the dual realization in terms of forms of this intersection pattern and perform the Kaluza-Cohen reduction to obtain a Lagrangian which displays the gauging structure that we had discussed in the earlier transparencies. So one way to the lesson to take home is that one way of realizing these non-abelian discrete gauge symmetries is to take p-forms on torsion homology classes which have these kind of relations or intersection relations. Perhaps a simpler second class of models, and perhaps also more interesting class of models where one finds these non-abelian gauge symmetry structures, discrete gauge symmetry structures, is to consider magnetized toroidal models. So consider just some compactification on a torus with some D-branes which are magnetized, or even heterotic models which are magnetized with a constant magnetization. So everything is really very simple. You have some constant field strength on the two torus, that's a basic toy model. So you have some gauge field which is linear in some of the translation directions. So the existence of a gauging in this kind of setup is manifest in the sense that when you do a translation in the directions of the two torus, like shifting x, one can see clearly that there is a shift in the y direction Wilson line of the gauge field. So the gauge fields are the Wilson lines of the gauge fields are shifting when you translate on the two torus. Now there is an algebra associated to this gauging, which is basically some Heisenberg algebra. So basically what that is telling you is that in the presence of magnetization, the gauge transformations in different directions don't commute with each other, as is the case in the absence of magnetization, but rather when you go around the two torus and find the commutator of the transformations, you generate a U1 gauge transformation because you're picking up the field strength via the circulation of the gauge potential. Now this gauge symmetry has a non-trivial this non-abelian gauge symmetry has a non-trivial action on the wave function of charged matter families that you get when you put open strings or compute the spectrum heterotic models in here. Essentially, the wave functions that have this structure, the zero modes, they have this kind of a theta function structure, which is just the sum of Gaussians, and they depend on parameters like the Wilson lines through this parameter set and U. So the two generators that correspond to the translations act as clock and shift transformations on this bunch of this multiplet of M charged matter families. So there is one generator that shifts one family to the next, and there is another generator. Sorry, there is an arrow missing here, which just puts different phases to the different families. Okay. So for each two torus where you have this magnetization, you have this clock and shift action, or this Heisenberg group, discrete Heisenberg group action on these M families of charged matter multiplets. Okay. By duality, this kind of symmetry is also present for models of the T-dual models of intersecting branes, etc. So it's something which is very toroidal, but very general for any toroidal model, in a sense. Okay. Now, what is interesting is that these symmetries are flavor symmetries in the sense that they commute with essentially gauge quantum numbers, but they depend on the family index. So they are family symmetries, and they have implications for, or they constrain the Yukawa couplings that you can find in these theories. And the computation of Yukawa couplings in toroidal model has been a substantial industry for a long time. So it's interesting to ask what happens with these flavor symmetries and how they constrain the Yukawa couplings. So there are basically two classes of examples, depending on what are the intersection numbers, or if you wish, what are the multiplicities of the different families that you have. So the first possibility is that the numbers, intersection numbers of different families are non-coprime, and the second is that they are coprime. So the prototypical example of having non-coprime intersection numbers, if you have three stacks of branes, and the pairwise intersection numbers are given by M, let's say. So all the intersection numbers in the model are just essentially 3. So one typical model of that would be the standard model where you have 3 families of left-handed quarks, 3 families of up right-handed quarks, and let's say you have 3 Higgses. Okay, so you have couplings like that, where one of the multiplets would be Higgses, the other would be left-handed quarks, and the second would be right-handed quarks, for instance. So what are the constraints that you get for these Yukawa couplings in this situation? Well, basically, if you realize these models in a toroidal setup with constant magnetic fields, etc., there is this discrete symmetry, which essentially is taking each family and shifting it to the next one simultaneously for all of them, and there is another symmetry which is rotating each family by a phase as corresponding to the label of that field. So the discrete symmetry leads to some selection rules, which is that the Yukawa is 0 unless the sum of these integers is equal to 0 mod m, and also the Yukawa coupling of families I, j, k must be equal to the Yukawa coupling of families I plus 1, j plus 1, k plus 1. So this symmetry was already noticed by Cremades, Ibanez, and Marchesano in the papers where they were computing these Yukawa couplings explicitly. So at the time, it looked like a coincidence that you compute the Yukawa couplings and they satisfy this selection rule. Later on, Choi and collaborators realized that, and Kobayashi and collaborators realized that these symmetries were associated to some discrete symmetry, but in their language it was not clear what was the nature of this discrete symmetry. In our analysis, it's clear that it's a discrete gauge symmetry and that this pattern will be completely exact. There is no effect in the theory that can violate these selection rules, not even non-perturbative instantons or whatever. Black holes, quantum gravity effects, wormholes, whatever. It's a discrete gauge symmetry, therefore exact in the theory. The second class of examples, which is more interesting and corresponds to these coprime multiplicities, would correspond to something more similar to the MSSM, where you have one Higgs multiplet, essentially, one up type Higgs, and only one type down Higgs, but you have 3 families of leptons. So the kind of Yukawa couplings that you have is just a single kind of Higgs coupling to, let's say, 3 families or m families of right-handed multiplets and m families of left-handed multiplets. And you have Yukawa couplings with only 2 indices. This kind of situation is realized when you have the left-handed families appearing from intersections in a single 2 torus, and the multiplicities or the different families associated to these right-handed fermions appearing from intersection numbers in a different 2 torus. So basically in this setup you have 2 independent Heisenberg discrete groups acting on x left and x right. So there is one group acting on x left and another different one acting on x right, and both of them commute. Okay, and the question is, if you are in such a situation, how can you engineer something which is invariant? You have something which is transforming the left movers, or the left-handed fermions, but not touching the right-handed ones. So how on earth can that be invariant? Well, the answer is that the Yukawa coupling can transform, because the Yukawa coupling depends on Wilson lines and things like that. And these Wilson lines are scalars that shift under these discrete gauge transformations, so they can transform as well. So the only way in which this thing can be invariant is if the Yukawa coupling factorizes in this way, with a part whose transformation cancels that transformation of the left-handed fields, and with another part which is devised to cancel the transformation of the right-handed part. So the presence of this factorized structure for the Yukawa implies that the Yukawa coupling has a rank 1 texture. So there is only one linear combination of the left moving fields which is coupling to one linear combination of the right moving fields, and those are the only massive fields. Now this was again observed let's say empirically or microscopically in the computation directly using theta functions, etc., by Ibanez, Marchesano, and Cremades in examples, and it looked like some accidental property of these models, and it was not clear whether you could violate it by doing different things, or what one should be doing to violate it. The message now is that this is following from some exact gauge symmetry in this configuration, discrete one, but an exact discrete gauge symmetry of the model. So this rank 1 texture is dictated by this symmetry, and it is protected by it, and there is no effect that can violate it. Instantons, wormholes, quantum gravity effects, whatever, nothing will violate it as long as you preserve this factorized torus structure. Okay, of course you can think about other perversions like twisting things so that you break this factorized torus structure, but in the model as it stands there is no effect that can violate this rank 1 texture. Okay, in particular one can think about instanton effects like those that Fernando was discussing in the context of F theory, where some faraway instanton kind of can induce some terms which were forbidden. This is valid in general, but in this particular toroidal case there will be conspiracies of different instanton contributions that lead to cancellation, because this rank 1 texture is again dictated and protected by this exact symmetry. Okay, so this model is hopeless. Of course you can of course again, yes?
In recollection, there were some loop killer potential calculations being done in those models, arguing that this could change the rank.
Well, the question is whether the computations were complete or not. So it's possible that you compute part of something and then this part of something violates the symmetry, but then the symmetry will impose that something else is around so that both things, all things conspire, and you get 0. And this rank 1 texture is perfection.
Couldn't you have couplings which are invariant under the symmetry, but then a field gets a VEV and breaks the symmetry?
If you do such things, you can do that. I mean, you can give a VEV to different things here and break the symmetry. That's fine. So that would correspond to modifying the model in some way, which would break the symmetry. So as I was saying before, you can do things that violate this factorization of two tori, like, I don't know, tilting the torus or changing some moduli that break this factorized structure, and then that could lead to violations of the discrete symmetry, and then you could escape this rank 1 texture. But the only thing I'm saying is that in this model as it stands, keeping it toroidal with this factorized torus structure, make it unavoidable that you have this rank 1 structure. Okay?
4 minutes.
Okay. So I'm about to get to conclusions. So essentially what we have been doing is spelling out the building blocks of abelian gauge symmetries, and this has allowed to propose a natural non-abelian generalization which is valid in field theory and was not around in the market. We have realized this structure in several classes of string models, for instance p-forms on these torsion classes, and also in magnetized compactifications, and in this later example they lead to very interesting implications for Yukawa couplings, for instance this rank 1 texture in certain particular models. I also want to emphasize that again, this thing is exact but very toroidal in a sense. So I cannot see any obvious way how one could generalize these kind of arguments to a theory where everything is curved and there is no natural notion of translations like in the torus, isometry translations like in the torus. So for sure the rank 1 problems that one finds in a theory are solved by a variety of mechanisms, as Fernando was reviewing in his talk. Of course, there are many further questions that one would like to answer. For instance, it would be interesting to understand more general discrete symmetries like R symmetries that were covered partially by Rat's talk in the heterotic setup. Also, it would be very interesting to understand in this more abstract language the non-abelian symmetries that have been studied in heterotic orbitals, and in particular they will require new ingredients because they typically involve the so-called quantum symmetry, which acts on twisted sector of orbitals, which is something outside what we have been looking at in a sense. Again, it would be interesting to understand further systems with gaugings. So the key ingredients in our setup was gauging of some isometries in scalar manifolds, and there is a whole industry of using gaugings to describe flux compactifications, and very likely in many of these compactifications you will find that some discrete symmetries are remnant. So it would be interesting to understand the implications of that, for instance for moduli stabilization and things like that. Again, there are other sources of discrete gauge symmetries which we didn't understand fully, for instance discrete isometries. You can imagine compactifying on a Calabi-Yau which cannot have continuous isometries but can have discrete isometries, and this is often done to make quotients and obtain non-simply connected Calabi-Yaus. But even in the covariant space, it would be interesting to understand the role of these discrete isometries and how they are encoded in the 4-dimensional effective action. It's hard to think about them as subgroups of some continuous group because the Calabi-Yaus don't admit continuous isometries, but perhaps in some sense something could be understood. In that paper we studied one particular case of compactifications on twisted tori where these things can be made very explicit, and one could see that one could describe the system in terms of these gauges, but that's because it's a very particular and simple manifold. One could imagine or ask the question of how to go beyond Heisenberg discrete groups. All the examples we found were associated in a way or another to Heisenberg algebras, and it would be interesting to understand why that's the case. Our guess is that that's because the simplest algebra that one can gauge, and then it would be a natural question to ask whether one can gauge other algebras and things like that. Again, also it would be interesting to go beyond the toroidal models, etc., etc. So as usual, and this is a general conclusion for this talk and probably for many others, there are many open questions in string phenomenology. Happily, I conclude with saying that many of them have been answered in this book that you are invited to visit in the Cambridge stand. Thanks.
Okay, before everybody forgets, the books are on sale, and any questions?
Similarities.
Yes, well, one of the examples, I mean, this setup of Wukov, Rangamani, and Witten, where they were interested in the ADS safety stuff, essentially corresponded or arose from the study of system of D3 rings at some set singularity, and there is some discrete Heisenberg group which is acting there. The kind of generators that they had is kind of exotic from our point of view in a sense, because there is one generator which is rotating the quiver, so it's acting non-trivially, mapping one factor in the gauge group to another factor in the gauge group. Okay, so it's acting as a rotation in the quiver, and then there is another generator which is acting as phase rotations of the different fluids. So basically one of the generators is this quantum symmetry of orbifolds that I was discussing about, and at least I'm planning to have a look at these kind of questions, because I think that would be another source of discrete symmetries which would be nice to be understood. Yes?
When you have extended cycles, the only particles that would be charged under the discrete symmetry are big extended objects.
Yes.
So is there any way around that other than the magnetized brains?
Well, for instance, this is typically what happens in these compactifications with torsion, that the charged objects are wrapped brains, and the strings are also charged wrapped objects, so everything is very massive, and it's not obvious what implications that would have for the real world. But for instance, in these abelian discrete symmetries for intersecting brains, when you do the uplifting to M theory, essentially becomes or turns into one of these setups with torsion cycles, only that some of the torsion cycles are collapsing. So you could think that perhaps in some regions of moduli space, some of these large cycles can go to zero size, and then these massive charged objects can become massless at that point in moduli space. So on those corners, you could have perhaps something relevant from the point of view of low energies. But generically, at the generic point in moduli space, it wouldn't be that interesting, perhaps. Only from an academic point of view, that there are these objects, you can do interactions with them, but you don't see anything at low energies, anything else.
Can I make a comment on that? I thought, well, we studied massive U1s in F theory.
Yes.
Then, it looks very similar what happens to how they get a mass there. It's again by these forms that are not closed, but it just looked like it was similar to your construction, but the charge was not, was just one. So there's no discrete symmetry associated to it. But under these U1s, these are actually open string U1s, if you like. They're just uplifted geometrically, and then the normal matter is charged under them. So it's not just, the actual standard model can be charged under these massive U1s.
Yeah, yes.
So in your case, they're a closed string on one U1. But when you uplift this geometrically to F theory, they're standard model is charged. In fact, the diagonal U1, we think, comes from these non-closed forms, similar to just a comment.
I agree. Yes?
Just follow up on what you're saying. So you're saying if you have an intersecting D6 brain model,
Yes.
that the 3 cycle you get upstairs from the Yukawa coupling is actually a torsion cycle. Is that what you're saying?
Well, basically what happens in the M-theory lift of these intersecting brain models, which have some discrete gauge symmetry, is that the open strings between the D6 brains become rough membranes, and these are the torsion cycles. And then the wall-sheet instanton lifts to some chain that makes k copies of these torsion cycles to be trivial. So the torsion cycles are the uplift of the open strings, and then the uplift of the wall-sheet instanton, if you wish, is a membrane instanton wrapped on the chain ending on these torsion cycles.
Okay, so before we leave, Joe has some announcement, but in the meantime, let's thank Angela again.